Thanks a lot. And I want to thank all the organizers for this great workshop and for accepting my talk. As Gerardo said, the talk is based on a joint work with Nicola Pinamonti, and you can find it easily on the arXiv. And it is about linear stability of semiclassical theories of gravity. Okay, of course, you know the topic, but just to give you a brief introduction, we want to describe the interplay between quantum matter and gravity, and a very nice framework where we're describing this interplay is the quantum Fit Theorem for spacetimes, in which we usually study the propagation of the quantum matter field phi over a classical globally hyperbolic spacetime. And let's say the dynamical equations which govern the backreaction of the quantum matter field on the background geometry are the semi-classical Einstein equations, in which the Einstein tensor is equated to the renormalized stress energy tensor associated to the field. And okay, you know again that there are several frameworks where one can study these equations, for instance, black holes, but another very interesting framework is cosmology. And in particular, in the last 10 years, there were some developments in studying the solutions of the semi-classical Einstein equations in cosmological spacetimes, namely in Friedmann-Lemaitre, Robertson, and Walker spacetimes. In particular, there are some papers in which the existence and uniqueness of local or global solutions of the traced semi-classical Einstein equations is achieved. And in this case, one considers the trace of these equations because you have a unique degree of freedom that is the scale factor of the universe. And in this sense, you can use this equation in order to study the evolution of the universe. And the idea is that this is relevant in physics, that since, let's say, you can expect that solutions of semi-classical Einstein equations and namely scale factors of this form should describe the evolution of the universe in the early stages, or alternatively in the inflationary phase. Let's say. And I want to point out that there is a paper made by Pinamonti, Simpson, and myself, in which it is proved that an initial value formulation for this problem can be made for local solutions, let's say, namely for scale factors that are supported in a small interval of time. And this result is achieved in cosmological spacetimes after rewriting this semi-classical equation in a new standard form. I don't want to talk about this paper, just to say that there were recent developments and many progress have been made in the last 10 years about this problem. Okay, and if you are interested in studying solutions of the semi-classical Einstein equations, then you probably meet the issue of runaway solutions, because there are some papers, in which it is argued that semi-classical theories of gravity seems to admit unstable exponentially growing solutions in time. Namely, solutions, physical unstable solutions of the semi-classical Einstein equations which diverge for large times. And this is of course a problem, because if you obtain runaway solutions from your equation, then this class of solutions might invalidate the research of global solutions for your theory, for your model. And in this sense, in cosmological case, for instance, it would mean that the universe would be unstable under perturbation. So you wanted to avoid this stuff. And the idea of these works is to approach the problem in a perturbative way. Namely, you consider the background spacetime G as the sum of, let's say, of the background of the zero order contribution G0 plus a linear perturbation H. And the idea is that if you see that this perturbation H diverges for large times, namely it is a runaway solution of your semi-classical Einstein equations, then you cannot assume that this background G0 is stable for large times. In this sense, you can say that the background is unstable in semi-classical gravity. And okay, this is the idea, and we want to investigate this problem of stability using a semi-classical toy model, namely a toy model which does not describe any physical problem, but it gathers all the main features of a semi-classical theory of gravity. This is the point. And our semi-classical toy model is of this form. we consider a quantum massive scalar field phi coupled with the classical scalar field psi. And we want to study in particular this couple of equations. In the first one is basically the Klein-Gordon-like equation for phi, in which there is an external potential, which is constructed from the coupling between psi and phi, and lambda is the coupling parameter. Whereas the second equation is a semi-classical equation, let's say, and in particular it involves the vacuum polarization of the quantum field on the flat spacetime, let's say. And the idea is that this system of equations should mimic the dynamics of semi-classical Einstein equations in a certain context, for instance, in the cosmological case. Our analysis consists on performing the linearization of the classical field psi according to the previous slide, let's say, and we consider then the psi field as the sum of a psi naught field, let's say the background field in this correspondence, plus a linear perturbation psi 1 classical. And the idea is to quantize phi in terms of this background field psi naught, and then to formulate an interactive field theory for the classical perturbation psi 1. We can make this step for instance, in the framework of PEA-QFT, and then to simplify the analysis, we can choose a constant background psi naught and the vacuum state in order to compute the vacuum polarization at the linear order. If you do that, you obtain this semi-classical equation, which involves the vacuum polarization at the linear order, and this on the vacuum state. And this vacuum polarization can be written explicitly and it is proportional to a certain operator Ka acting on the perturbation. And this operator Ka has this form. It is basically composed by a D'Alembert operator plus a number plus a constant A, which at the end of the story, it describes the renormalization freedom inside this construction, and this D'Alembert operator is applied to this integral of the retarded propagator weighted by a spectral function, let's say rho, that has got this form. Okay, computing this vacuum polarization, we want to study the following four-order differential equation psi 1. That is a semi-classical equation and corresponds to the previous linearized equation, plus after adding, let's say, a classical source F. And you can notice that this is a four-order differential equation psi 1 because it involves a D'Alembert operator applied to this operator Ka, which contains another D'Alembert operator. In this sense, this differential equation mimics very well the mathematical structure of a semi-classical equation because it is a four-order differential equation. The steps of our work are the following. In the first step, we show that past compact solutions of this equation respect causality, namely the support of psi 1 is contained in the causal future of the support of the source. Then we construct the retarded fundamental solutions associated to this equation, in particular, let's say the retarded propagator associated to this equation. And thanks to this retarded propagator dr, we are able to construct the past compact solutions of this form, namely after applying the propagator to the source. And then we can show that these past compact solutions decay at 0 for large times, which means that they are physical solutions and they aren't runaway solutions. Finally, we are also able to show that if you consider the linearized equation written in this form, namely without the source F, this linearized equation has a well-posed initial value problem. And after imposing some initial data, compactly support initial data at the initial time, and for a wide range of values of the coupling parameters of the model. I have no time to discuss the details, but more or less these are the results. In particular, the main result is to show that an initial value problem for this model can be formulated, and in particular, the stability of the linearized backreactive system can be achieved. In particular, if you consider spatially compact perturbations, massive quantum fields, and compactly supported initial data or alternatively source, then you can prove that there are several choices of renormalization constants of the model, such that the linearized semiclassical solutions decay to zero for large times. And in particular, you can show what is the behavior of these solutions for large times. In particular, you can see that these linear perturbations aren't runaway solutions, but they are basically a superposition of plane waves. You can see that, in particular, that the frequencies of these waves are depend, let's say, on a mass me that is fixed by the normalization constants, more or less. And the number of solutions depends on the initial data. Let's say you can have 2 solutions, 4 solutions according to your choices. What is the idea of this work? Is that this model should mimic, or at least there is a formal correspondence between this model and the semiclassical Einstein equations for instance, in cosmological spacetimes. In particular, the equation we have studied, namely this equation, these linearized equations, correspond to the linearization of the semiclassical Einstein, of the traced semiclassical Einstein equations after adding a classical source, let's say. For instance, you can, in a stochastic approach to gravity, this equation should remember the Einstein-Langevin equation, for instance, in which you add a classical tensor tau, which incorporates fluctuations of the stress energy tensor. So the idea is that this model mimics the dynamics we have already studied in cosmological spacetimes, and in particular, this formal correspondence is obtained if you, let's say, if you put in correspondence the coupling parameters of this model with the parameters you usually meet in semiclassical Einstein equations. For instance, the lambda, the coupling parameter lambda, correspond to the xi parameter, that is that measures, let's say, the coupling between the Ricci scalar and the quantum field. G1 corresponds to the inverse, basically, of the Newton constant, and so on. So in this sense, studying this toy model, we are able to guess the behavior of the solution of the linearized semiclassical Einstein equations, at least showing that even a well-posed initial value problem from global solution can be formulated. This is not a real result in the sense we are only guessing the behavior of these solutions, but according to the result we have obtained in this toy model, we are quite confident that something can be made also in physical spacetimes, in particular in the cosmological case. I'm at the end of the talk, so these are basically the future outlooks of our work. In particular, we want to study the linearized solution of semiclassical periods of gravity, and the idea should be to, let's say, to combine the results obtained in this toy model with the ideas we have developed in cosmological spacetimes. So in this sense, combining these 2 papers, we would to infer the stability of linearized semiclassical solutions in cosmological spacetime for the semiclassical Einstein equation. But I mean, this is future. We have to do that, and so. But I mean, it would be a very nice result, in my opinion. I have no time to discuss the details. I'm basically at the end of the talk, but please, if you are interested in further details, send me an email or write me on Slacks, as you prefer. So for the meantime, I have finished. So thanks a lot for your attention.
Thank you a lot, Paolo, for such a wonderful talk. I guess we have some questions. There is one question from Dan Jansen. Please just unmute yourself and ask a question.
Hi, Paolo. Nice to see you.
Hi, Dan. Hi, Dan.
Well, the image is not great, so let's.
Don't worry.
So well, we also had a bit of a discussion about this back in Genova when I was.
Yeah.
I'm trying to remember some of the things, but am I right in recalling that if you put the story on a compact universe, you will still get these runaway solutions?
Yeah, I think so. I'm not an expert about complex spacetimes, so I'm not completely sure about it. But Yeah, the point is that of course, if you consider compact support initial data, maybe you have some problems in formulating a physical relevant problem. I mean, but I think that the nice result is that if you obtain this stability if you consider an equation of this form in which you have a compactly supported source, and I think
but isn't in this case sort of the degrees of freedom that source the other, so to say, that they in a non-compact universe they sort of fly away to infinity and therefore become less pronounced, but in a compact universe they keep sort of circling around and they keep sourcing the other degrees of freedom and things will blow up.
I mean, in this case, we are interested in globally hyperbolic spacetime. So in this sense, I think that at this stage is we want to study, let's say, spacetimes such as Minkowski's, the Friedman.
But I'm thinking about Friedman-Robertson-Walker spacetime with like spherical spacetime.
Of course, in the closed case, it is a good point. I mean, I don't know at this stage if what is the answer in the compact case. I mean, but of course it is of interest to investigate this case, but at this level, I haven't an answer, to be honest. But yet you're right. There might be a problem in this case. Yeah.
Okay, thank you.
Yeah.
Okay, thank you for the question, Dan. Do we have any other questions? Okay, Antonio, please.
Yeah, thank you for your talk. It's very interesting for me. So if I have understood it right, your existence of non-runaway solutions depends on the arbitrariness under your renormalization scheme. Is that right?
Yeah, you're right.
Okay. So have you maybe realized that these renormalization parameters depend? The values that allows you to see that there is no runaway solutions, the values are maybe near to some physical scale of the.
Yeah. Thanks, Antonio. This is a good point. We have guessed some values for these parameters for instance, in the semiclassical Einstein equations in cosmological spacetimes, and we have noticed that. There is a problem in the sense that, according to our analysis, there might be some issues because m squared, for instance, should be very large in order to obtain our results. Okay, I want to stress that we fix sufficient conditions, so there would be other choices of parameters such that you obtain stability, but in principle, the values we obtain are not so physical. I think instead that the very nice result is obtained when you study the semiclassical Einstein equation with the source F. Namely, if you consider the semiclassical Einstein equation with another source inside. In this case, you obtain stability for physically reasonable parameters. Namely, the mass is quite small. Let's say let's say it can be related to a physical quantum field. I mean, psi can be zero or in the conformal coupling case. So if you look at our paper, we have put a discussion about this correspondence from a physical point of view.
Thank you. I got also a related question to this one.
Yeah.
This condition of the absence of runaway solutions does not uniquely fix these renormalization constants, right?
You're right. Yeah. Okay. The point is that you have a wide range of values for the renormalization parameters. Exactly. Yeah.
Okay. Thank you.
Yeah. You're right.
Okay. So let's thank again Paolo for this wonderful talk.